So we've spent a lot of time talking about plate tectonics and the hypothesis of continental drift. But this video is going to focus on the scientific evidence that we've used since the 1960s to really better understand the theory of plate tectonics. A lot of the scientific evidence that we now use to support that theory of plate tectonics comes from deep sea ocean drilling. This is really different from drilling for like oil. Instead, this is scientific drilling where they're collecting soil, sediment, and crust from underneath these ships. With this, they're not only going to look at the sediment and the rocks, they're also going to look at the fossils inside of them. But they've noticed that when you're moving away from the spreading center in the middle of the divergent boundary, that the age of the sediment and the rocks are getting older and older as we move away from that mid-ocean ridge. They've also determined that the sediment becomes thicker the farther we get away from the ridge. And one of the most interesting things they found is that regardless of where we are on the Earth, the oldest oceanic seafloor they found so far is only 180 million years old. Remember, the Earth is 4.5 billion years. So where is all of this missing oceanic seafloor? And we'll come back to this. While they're not directly related to plate tectonics and the boundaries between plates, another piece of evidence we can use for the theory of plate tectonics are hot spots that come from mantle plumes and the island chains that develop on top of these hot spots. So if we look at the island chain of Hawaii, these are just chains of volcanic islands that are above the ocean. But if we look at the ages of each of these islands, we'll see that as we go from the big island of Hawaii and we move farther and farther away, those islands are getting older and older in age. And that's because the Hawaiian Islands sit on top of a hot spot. This is just one location or one spot on the Earth that for some reason is just really hot. So we have magma that plumes or just has a constant flow up towards the surface. So there will be a plate sitting on top of this magma plume that stays in place. It doesn't move, it stays in one spot, but the plate moves along on top of it. So that over time, as the plate moves over the hot spot, that hot spot will create a series of volcanoes. And if those volcanoes are tall enough to get above the ocean, we will call them volcanic islands. But another type of evidence that we use to support this theory of plate tectonics is something that's called paleomagnetism. And this just means ancient magnetism. And this all has to do with magnetic field around our planet. Today we have our north geographic pole and our south geographic pole. What we would think about with, say, Santa at the North Pole and Antarctica at the South Pole. And today our magnetic and our geographic north and south poles line up. If I took out a compass or opened the compass app on my phone, the needle would point north, towards our north geographic North Pole, which conveniently today our magnetic north is in a very similar location. But over Earth's history, our magnetic North Pole has been able to flip. So instead of our compass pointing north, our compass would point south during a period of magnetic reversal. And we can actually look at the rocks along our seafloor and to determine whether they formed during a time of normal magnetic polarity that we have today, or a reverse magnetic polarity where it would point towards our geographic South Pole, towards Antarctica. And the way we can do this by looking at the rocks is because igneous rocks that have iron in them, the moment that they turn into a solid rock, they lock in the position of Earth's magnetic field. Because those minerals are actually going to align themselves to the magnetic field, just like the needle of a compass does. So we can look at older ancient rocks and figure out where our magnetic north and south poles were based on the way that these minerals lined up. Again, just like the needle of our compass pointing towards a pole. And we just call this paleomagnetism. The rocks are telling us what ancient magnetic fields were like. So if we look around a spreading center, we can see kind of stripes of magnetic reversals. And this was discovered in the early 1960s. And this is because at a spreading center, as those two plates diverge and move away, magma is going to move up and solidify between those two separating plates, creating new lithosphere. But as that magma cools down and solidifies, it locks in Earth's current magnetic field. It's going to make the minerals align that way, like the needle and the compass. But over time, that spreading center is going to continue spreading. So if we look here on this image to the right, our green layer is being created first. But as that divergent boundary continues to be pulled apart, we'll have a magnetic reversal happen. New lithosphere will continue being created between these two separating divergent pieces, but it has a different magnetic field. But then over time, if we go to the very bottom of that image, we've had another magnetic reversal occur. We still have divergent boundary pulling this apart, and it's creating these alternating kind of sequences between normal and reverse polarity. So it's symmetrical on either half of the spreading center.